Let's start with my talk. My talk is called The Next Decade of Industry 4.0. And let me first say how it was evolving. Actually, I gave the first speech in front of our Chancellor on the 3rd of July 2011. You see, the first 10 years have now passed. And what I said was, just abbreviated part of this, remaining a producing country today means getting fit for what we call the fourth industrial revolution. By the internet. It's based on internet technology, Internet of Things, a cyber-physical system, and there is a, as Regina pointed out, a fundamental, change in the architecture and the paradigm, because now the product itself controls its own production system. And many people were shocked when I said this for the first time. It monitors the relevant ambient conditions via its embedded sensors, triggers countermeasures if there is error or malfunctions, and the product itself becomes the observer, but also an actor. This is new, and Professor Masik always followed this paradigm of multi-agent already, and this is based, without AI, you cannot do this fourth industrial revolution. And our Chancellor picked it up. She gave a speech directly after this, but it was not in her manuscript, but they said, excellent idea, we should go on and so on. So, and there were 2,500 executives, so it was a good chance to promote this, and actually the idea catched up. Today, we counted last year, we have more than 100,000 publications on this topic. This is quite good, all mentioning this. Also, the investment in Europe per year, not by funding agencies, I must say, by industry and funding, is 140 billion euro per year. In Germany, we are very grateful that our government last year started a new funding initiative with a focus on industrial AI, 7 billion euro for research for a small country like Germany. It's quite a lot. And I must say, it's good that we have a term with Industry 4.0, which is recognized internationally. Most people know it, like Autobahn, kindergarten. There are not too many words which are from the German language. And just this week, on Monday, we met in Hanover. Hanover Fair is the biggest fair with 2,500 exhibitors, which shows tools. The US was also very present. This year we had Portugal as a guest country, but 2,500 exhibitors with tools, software and hardware, and solutions for Industry 4.0. The slogan was, let's create the industry of tomorrow. So it fits to what Regina just said. This is also the idea of the workshop. And 3 professors, I did the research part, Professor Kagermann, who is the former CEO of SAP, the biggest software company here in Europe, and Professor Lucas, he came from the political side. He helped us a lot, Big science is also connected to big politics sometimes. And clearly, if you go to such a high volume, you have to have the politics with you. I was there are also participants from Cincinnati, and the city of Cincinnati was the first to pick this up. Actually, the mayor signed a contract saying, we are the first demonstration city in the United States, Cincinnati, for Industry 4.0, very early. Or when you go to Tesla, as I said, to the factory, they have even on the business card, they have Industry 4.0 liaison officer. So also Elon Musk picked it up, and even in China, the word is written in the German style. We always do this with IE, which is not the English version, to show that that concept was coined there. Now let's go to the content. Why did we do this? What is the motivation? And the motivation is a social, let's say, social economic motivation. First of all, we have the aging society, we have a later retirement, maybe a must for economic reasons in the near future. So we have to see what kind of workplace can we offer also for aging people. And here the collaborative robotics comes in very much. I will show this later. We have a lack of skilled workforce. Yeah, we have not enough workers for manufacturing. But the most important trend is that mass customization. The individualization is one of the key motivations for consumers to buy something. Yeah, this was always in the United States, in Europe, not so much in Asia, but Asia also has changed. If you go to Japan, they also want to distinguish each other. They want to have a very special, customized product. So low volume, high mixture factories. And this is a challenge for the technology because you have to have multi-adaptive factories. You can no longer build a factory which is, for the next 20 years always does the same. You have weekly changes in your manufacturing environment, and this is for the robotics community a big challenge because you cannot have a constant, very simplified environment. The system must be highly adaptive. Shorter product cycles, increasing variability of the products, and then as we experience it right now, the volatility of the market. This is really crazy. During the last 10 years, everybody doing manufacturing complains, of course, yeah, but this is a fact, a true fact, so we have to see. And then, at least in Germany, and now, but also I think starting very much in the US, the question of green production, urban production, the ecological, that we really have to have a circular economy, resource efficient things. In Europe, we all have to do the so-called Green Deal. Our commissioner has, told us everything must be clean, and I will discuss some of the technical aspects behind this. Cobot and softbot are key elements of our strategy. That means we want to have workplaces where there is physical but also cognitive assistance for the workers. And I go even so far that I say what we need is not more the home office. We have enough of this during the pandemic, and home office cannot help us in manufacturing. It's not office work, not Microsoft Word or PowerPoint at home, but it's really working. And how can you do this? And we think that we can have a home workbench in a pandemic or a crisis, in a natural disaster, in war situations like we have now, that the production can go on in a remote place. And we have the technology which we can install. We are working on this. I think it's very much important. And I think in 10 years when we meet, we can have homework benches. Yeah. And next thing is urban production. We started very early. The first factory worldwide for urban production was opened already in the first year because I already announced this concept to some industrial companies, especially family-owned. In Wittenstein in Stuttgart, it's a middle-sized town in Germany, we have a factory which is in the middle of the residential area. Yeah. Let's say 20 years ago, you would have a protest of the owners of these houses and so on. But this factory is more or less emission-free, very low emissions, very low noise, 35% of saving energy and so on. And the good thing is, and that's the idea, key idea, because urban production means the workers can walk from home or bike to the factory. Today, the reality, at least in Germany, Mercedes, for instance, workers have to go 1 hour at least. And I know in Silicon Valley, yeah, when you live in Santa Cruz or, even San Jose to go to Berkeley, have traffic jam and so on, 1.5 hours in the car. And this is pollution. You want to go to your workplace. So, 100 years ago, when you go to a city like Prague or Berlin, you see the factory in the middle of the town. But this was, pollution all over, so we stopped this. Then we had it outside of the city, and now it comes back. Why? Because we have the technology to make clean production possible. I think this is a very important idea for the ecological factory, and but that's not all. So we started, and this is a necessary condition, of course, that all the equipment and the people working in the factory are connected. This is the industrial internet. But I must say, there was a misunderstanding that if you have industrial internet, yeah, Cisco delivers all the boxes to have internet in the factory, nothing really essential will happen. I mean, the bits and bytes go faster, but this is not what we want. Intelligent manufacturing is much more. So it's necessary, but not sufficient. And some companies, I must say, this is not a criticism of a single company, but some companies went in the wrong direction. They were thinking, I just need the internet platform and then that's it. This is not intelligent manufacturing. For instance, General Electric went a little bit in the wrong direction. We need at least a semantic communication, interoperability between the machines, because if I just get a string of bits, we all know in computer science, this doesn't work. The machines have really to have semantic understanding of what is going on here. But even more important, I say 30% is really the architecture, cyber-physical production architecture. That's the software layer above all the communication layers. And then, most important, and therefore I think we selected the audience also in this direction, I personally think that, of course, robotics, especially team robotics, where various different robotics with different skills working together and also working together with teams of people. This is the most 40% of the business is in this direction. So unfortunately, there is nobody from Cisco here. If you only have Cisco cable and routers, this is good, but it's not enough. This doesn't do the job. The research should go into the other areas. Yeah. And in the long run, we even go further, and I think Professor Mazik and Professor Bakshi always said this. We need, of course, more autonomy. We want not the human-less factory, but we want to have a factory which is autonomous in the following sense, that you can give the factory control system a certain, let's say, a key deliverable. I want to say, in 1 year, this factory should be more energy efficient. And then the system, autonomous, yeah, takes the measures like a good manager to achieve this goal. So it's a long-term goal. Right now, in robotics and AI in general, you have very short-term goals. Yeah, you can say in the next 10 minutes, please do this and achieve this goal. But you cannot say, follow a long-term strategy where you may have also some backlashes and so on. This is real, the long-term story, and we are now starting to work on this by deep learning and deep understanding for long-term autonomy. And I haven't seen a lot of robots. I mean, the Mars robot is long-term in a sense, but he follows always very predefined goals. It's not really what I want to see. It's a good start, but it should go on. Now, back to the infrastructure. I think we need, edge computing already, because when it was a failure to go to cloud computing completely in manufacturing. This doesn't work. And you see it here in CIIRC in the presentation, because it's real time. I mean, there are a lot of real time demonstrations with the robots. And of course, online machine learning in real time is only possible if you don't go for every step to the cloud. It's too slow. And with the 5G and 6G, we have now, you can see it down on the floor, we have now real-time guaranteed latency. So we can really have the real-time control. Second is what we call fog computing beneath the cloud. We can push some of the information we get from field devices on a little bit higher level to do more refined data analytics, but still in the factory. This is called fog computing. Then cloud computing, I think everybody knows here. This is good. I'm not against it. We need it for supply chain management. This is not in real time. big data analysis, and so on. And finally, what is new, and this comes from Berkeley, is the idea of sky computing. It's pretty new during the last 2 years, and this is, above the clouds. It's the worldwide network, and this is very good here in the international conference because we see that we have to work all together. You cannot invent some intelligent manufacturing without having the international perspective, as I said at the beginning. So manufacturing ecosystems will be distributed, of course, and here the sky, which is above the clouds, is a virtualization of all the cloud systems, is extremely important. Why? Because now we have a fragmented system. Every cloud system has its own apps, and especially for manufacturing, this is really very expensive. There are, for instance, if you go to the Amazon cloud, more than 175 services, but they are not compatible with the Azure cloud with Microsoft, or you go to another cloud by Google, it doesn't work. You always have to reprogram, and this is not the case on the sky level because you have another virtualization level, and we experience this. I think this is the future also in the next 10 years, so it's a long-term program. Now, both sides, the autonomous systems with edge and fog, and the systems where you still need human intelligence, of course, this is more the business side of the game, is shown here. If you think about new supplier networks, logistic networks, and so on, this cannot be fully automatic. I'm convinced, business is something also for humans in the end. You can dispatch some parts, but the real, to open a new business, you need the design, the plan by humans. But then if you deliver and operate these systems, of course, you can go to fully autonomous systems for routine tasks, and there you need the edge and the cloud. Here I show you our new architecture for the next 10 years, because we think we have a very important middle layer, which we call the digital twin layer, because we go so far that every component in manufacturing, every tool, every process has its own digital twin. And digital twin means this is like the diary of this physical object. A virtual copy, but not only a memory. It also can be active. If something goes wrong, the digital twin complains. It's too hot here, it's getting, or I get wrong signals and so on. So the digital twin is really a twin in the sense, is a companion getting active. And this is for, starting by the design up to, maintenance repair. This is what previously we had the old PLM systems, product lifecycle management, but these were very primitive database systems. They are still in use. But we will switch them off, I think, in the next 2 years. Most of the companies will say, this is the digital twin layer, is much more, sophisticated and really can deal with a problem in a intelligent way. Very important for digital twin-based architectures is, of course, the asset administration shell, because this something which, as I said at the beginning, controls the complete production system, production process. Even the robot can ask the digital twin, where is a good gripping point? And this virtual object will say, this class, please grasp me here. So the robot has not the task, to find out, but the object. So it's kind of, as I said, a paradigm shift in manufacturing. And so we need this, and we already have done it. At least in Germany, we have now a standard, because standards are very important in this context, because when you go from one manufacturer to the other, of course, you don't want to exchange the digital twins always. So, for instance, here you see that each asset has what we call an offered capability. and of course a robot has many, but for instance, the grasping device is my capability. I can grasp up to 50 kilogram, with this kind of gripper and so on. This is a typical capability. Then the robot is part of a production cell. The production cell in a holographic way has also a capability, which is used to select this cell when the process goes on, and so on. So you have offered capabilities, and of course, when you want to manufacture something, you have the specification of which capabilities are needed. So it's like a marketplace that, the object goes, where is this service? Where is this capability offered? And then this production step is done. This is a general idea, and here you see a very simple example of the specification. As I said, this is a standard, so various companies are already using this in manufacturing. So you have, for instance, here the product says, okay, it's about the production of assembly of a car door. It's the material is metal, what is the weight, and so on. And the resources I need is a magnetic gripper between up to 15 kilograms, and then the capability is really what the offered capability is what is required. And so it's a good match, and then the system really starts to work on this. What is also very important, I said we have to retrofit. That means to change the manufacturing devices more or less in a couple of hours. And this we coined the term plug and produce. We plug a new tool in and the production starts immediately. How is this done? It's not only physically. Here we plug in a simple mechanical pressing station, and this station comes, you fix it, but then immediately in the next few seconds, the ontology describing what this device is offering as a capability is inserted. So we can start right away. We have a lot of demonstration and people are also shocked. Traditional manufacturers don't understand that. They say, I have to program this and so on. No programming necessary. It's kind of low code. You start this because all the information is already coming with a digital twin of this new device. And of course, there are now many platforms. I just gave some from Europe. Of course, we have the hardware platforms, interoperability platforms. I'm sure you have heard about Gaia X is a big initiative with more than 2,000 companies. Here, CIIRC is also involved. We have a special new organization in Europe for industrial AI, which I helped to form, the AI Data and Robotics Association. And we have special special areas in production, like automotive production, have the Catena X consortium. So I think it's well organized. Now the central question of Regina, what are the goals for the next 10 years? And I have here made a list of the most challenging problems here, characteristics which we still have not completely achieved or just are beginning the research. And then in the next, you see these Lego bricks. These are the solutions from AI which have to be deepened to fit and to solve this problem. I cannot go through all of them, but let me say online quality control, for instance, incremental quality control. Of course, we need active sensor fusion in this case. We have very cheap sensors. The factories, if you compare factory 10 years ago, now it has a 10-fold number of sensors in the factory because they are very cheap and they are connected. It's very simple today with 5G to connect sensors. And of course, but we have to do the job. We get data, but then what do we do? The interpretation of the sensors is important. And here we use deep learning together with special active sensing technology. For the digital twin, as you saw, we need advanced knowledge representation, which fits manufacturing, or when we want to do hybrid teams of robots and workers. Of course, one of the biggest problems is plan recognition. We also have to make sure that we can predict the next steps of the human worker. The human worker is a big question. The robots are more or less deterministic, but the human behavior must be, predicted or at least understood to do the right action by the system. Of course, we need data sharing efforts. I showed this here, from the component suppliers, the machine suppliers, to the factory operator. And this is, again, the idea that only with data sharing we can do very large, what we call now transformer-based models in neural network technology. I'm very proud that we have the first excellent results in this way, and that I know a lot of big companies which actually follow exactly this triangle approach. Let me give you one specific example, one use case very shortly. It's a company which is leading in valve production. So you see all these devices here. These are the valve for oil, water, what have you, in the chemical industry and so on. Here at the valve, the first step is to try to design new products which are intelligent themselves. So you inject some AI into the valve. For instance, these valves now notify pumps that they are closing. This was not possible before. I mean, the pump would, see that if it pumps oil, there is a valve, it cannot go on with this. But now there is really a communication with this new kind of cyber-physical valves. Then we have the next thing. We provide smart systems, complete systems with such a valve system. We have also assets like maintenance of the valve or other asset management problems. Again, AI systems on top of this. And then finally, this company now also makes money with smart added value services. They say, okay, we can now give you a remote tank management. If you have a lot of tanks with oil, let's say, or gas for at an airport, for instance, or what we see now in Ukraine with military aircraft, you need a lot of gas, of course. You have tanks, and you want to have a good farm management of all these tanks. And this is also with this type of construction, with the digital twins of the valve, they do this. So they have a new also business, not only the hardware valves, which are now intelligent, complete solutions up to added value. I think this is a very good business model, and the company is flourishing. 4,500 employees, and only with valves is quite a lot, because they are quite expensive. And so our strategy in Germany is that we inject more and more intelligence in the most important products, which we are famous for: manufacturing equipment, cars, medical equipment, and agricultural things, and of course also aircrafts. Now let me go into one subject, finally, also in a little bit more detail. This is a topic for a new project which we are just launching. Actually, we are starting this summer. Everything we prepared. We have the first demonstrators for it. This is, we call it IQAMA. This is a real-time production monitoring for zero error or zero defect manufacturing. And the completely new idea is that we really watch the actions before the error happens. Traditionally, quality management, you measure, the product and see some deficit, but then it's too late because the error already happened. What we do, we watch the humans, the robots, human-robot interaction, human-human interaction, robot, and so on. Everything, is analyzed. And as soon as we see something is going wrong, stop. And then we can, repair, and this is very cheap, because if you do it instantaneously, it's much better than if you do it at the end. Of course, we need cameras, wearable sensors, IoT devices to do this. Again, it's multi-sensor fusion, but it's also plan recognition, interaction recognition, and so on. So the general idea is that we have, when you go through all the production step, and if there is an error in step K, normally, I was at BMW at the factory. You see, they do a final check. This lasts 20 minutes per car. In this 20 minutes, they always find some small error glitches. Then they go back to the production step. Sometimes they must disassemble the car because they cannot access the error part. And so it's a lot of time, energy consumption, produce a lot of waste and scrap. And with the new method, we have this small, you see all the small loops here. In each step we check, and then if we go to the end, there should be, in the ideal case, no final check necessary, no defect. And at Hannover Messe, just last week and this week, we show a new system because we are often asked, manufacturing, what about AI for good? Is this also for the society? And as I said, the urban production is the first step, but we also did something, we used the same technology for the handicapped. In Germany, we have more than 300,000 workers with Down syndrome. And these people, unfortunately, have problems with the memory. If you tell them, please fill in 10 nuts and bolts into this package, and that's what they do mostly is packaging, then they have problems in counting. Sometimes they fill in only 7 and so on. How can you do this? And we use exactly augmented reality and our quality check. We project on this table, the nuts and bolts, and they actually like this very much. We did this now in 3 factories for a couple of weeks, no error, because the people, just get this, and the system, as soon as something wrong, it gives a signal, and then they can redo in a very friendly way, and they like it. So it shows that this technology, we always ask AI for good, what is the benefit? And I think here is a very good demonstration case that this technology helps also the handicapped and disabled people. I cannot go into the detail, but I think everybody here understands it, that you can track the movement of such things. I skipped this. Let me come to the end very soon. In principle, from a basic research point of view, I think what we need is even more cooperation between the numeric part and the symbolic part. Because a perception, of course, without analysis and numerics you cannot do. This is very clear. Sensor fusion, predictive maintenance, online quality control, everywhere, you need this very numeric problem. On the other hand, the digital twin or team action planning, even motion planning, is more symbolic. Symbolic equations have to be solved, and also safety control. So what we need is that also we learn not only from data. I always say we must learn also more from conversational learning. I'm a big fan of big data analytics, but I agree also with CMU, especially my colleague Tom Mitchell, who says, this is bullshit. People learn most not by own experiments. If you want to reinvent all the physics, this is impossible during lifetime. Maxwell's equation, you better read a book on physics and learn this, interactively. But automatic learning only from data, also it's good for many applications. It's not good for the scientific understanding of these things. So this has to be done. This is human-machine conversation and then extracting. And actually CMU has very good software which can already do this. We are also working on this. And the second thing is I learned most from reading textbooks, Berkeley physics course and so on. You read and hopefully understand. And it is better than doing the experiment and then reinventing natural laws. This is, I think, a big mistake in AI, a little bit too much hype in just data-driven learning. I don't want to criticize this, it's absolutely important, but we should also look to other, what we call knowledge acquisition strategies. And all the 3 channels have to be used in my mind. In summary, I think the next generation of researcher has to look in intelligent manufacturing very much to autonomy, but also to interoperability and, as we heard, sustainability. I think the sustainability and climate change issues are also pressing, and of course the manufacturing industry is always criticized a little bit in this dimension. My last demonstration here is to show you that this really works, we have, for instance, an installation at Airbus in Bremen. And here are 4 robots. Actually, the table itself is also a robot, a mobile robot, bringing 2 other robots which are installed here. And then there is a mobile robot which has the tools for the worker, and there's 1 human worker. And the task is to assemble in a wing the so-called raceways. These are channels for the hydraulics and the electronics in a big aircraft like the Airbus 310 here. And you see the worker gets help from the cobot. It gets at the right moment the right tool. This is a special screwdriver which is also connected to the internet. You could say, why doesn't the robot do the screwing? This is not allowed by law in the aircraft industry, because the right torque, actually the worker has to sign for every screw which is fastened. He has to sign that he did it with what kind of torque and so on, because it's very dangerous. If a robot would do a little bit error, there would be a crash later. But the worker does a lot of overhead work, and this is done by the robot. The robot is actually fixing the part which has to be screwed, which is good. So it's a good split of work. The robots help physically the worker, because normally these workers, this is the real Airbus installation, can do this for 2 or 3 hours per day only. Otherwise, they have problems with their neck and so on. It's very tough work. And we gave a similar demonstration at Hanover. Just this photo is from Monday this week with RICAIP, where we show a little bit already this, what I said, the intelligent workbench for homework, or where somebody from a remote place using virtual reality, augmented reality, actually is helping to teach a robot, but not the normal teach-in, but to teach how to cooperate with a human. Collaborative has to be also learned. What can you do together? And here is my conclusion. I think that export success is still based on physical products. I think it's a big error. You see this on the stock market. If you only believe in social networks and so on, this cannot, because we see this also with Bitcoin and so on. There is no value behind it. Without physical products, I think our economies will not survive. This is something politicians have to learn, and some of the people on the stock market also, they learn the hard way right now. For interoperability, I think industrial AI components are really very important to be standardized and certified. Active digital twins are extremely important to establish a circular economy. Deep learning, as I said, is not enough. We need hybrid AI systems. And let me just say, hybrid teams of robots, cobots, softbots, and people. These are really in my mind, the key issue. And I think we are the right people here with all the young people to solve this problem, together with Regina. Thank you very much.